Okay, hello one and all, and welcome to CS50's very first SuperSection for week 1. My name is Carter Zanke. I'm the course's preceptor. I'm joined here by many of our wonderful staff members. I'd like to stand up and say hello. Yeah, round of applause for these folks. They're wonderful. They'll be helping you through this SuperSection today. This is our first SuperSection for the course. On a normal week, you'll actually attend your own section led by course's head teaching fellow. You sign up for those on Mine at Harvard, and you'll attend those starting next week. But this week, given the odd schedule, we thought we'd come together for one large section overall. So here are these details here. You're welcome to email us if you have any questions, heads@harvard.edu right here. And all of our slides and materials for today will be at this URL down here on the course website, going to the SuperSection page there. To kick things off, though, I thought we'd actually have you all talk to each other and think about these two questions. So think back to lecture and think about this first question. What did you find exciting from that lecture? And what are you still confused about? What do you still have questions about? So turn to somebody, perhaps who you don't know, and talk about those two questions for 2 minutes here. 1, what are you excited about? 2, what do you still have questions about? OK, let's come back from these conversations. So glad you all are having this wonderful discussion here. And let's hear from a few different groups on what you were thinking about for these questions here. Thank you all. Let's actually turn to this maybe left-hand section. Could one group over here tell me what you're excited about for this week and one thing you're still wondering what you have questions about? One group from this side of the room. Could I narrow it down to somebody from the front row, perhaps? What are you interested in? What do you still have questions about for this week? Yeah, go ahead.
I think it's more of the less of the code and the syntax itself, because that kind of picks up quite quickly. I think the hardest thing is probably how you think how to construct efficient code. You sometimes just have to think in a different way.
Nice.
And that's something that I guess will really take some time to come to terms with.
Totally, yeah. So there's this question about how do you write efficient code. And later today, we'll actually work on the course's lab, this practice problem, to help you see how we can write efficient code in that instance. You can work together on this practice problem and get ideas from each other as we go through. Let's hear from maybe one more group over on this side, maybe somebody in the second row back here, if you don't mind. One thing you're interested in? Yeah, go ahead.
I'm really interested in also kind of those patterns of thought, but also creating stuff.
Mm-hmm.
Coding is really cool to have the final product, and now I'll get to have the tools to make the final product.
Yeah.
And yeah, something I'm confused about is actually I feel like there's so much syntax to learn, and that's sort of giving me pause. It's like, how do I even know what's out there? I think somebody mentioned it in the orientation. Like sometimes students will code something all the way out because they don't even know that there's a program for it already.
Yeah, exactly. So there's this idea of how do you take this idea you have and what you want to build and turn it into the syntax, actually write to make the computer do what you want it to do, right? So all these are good questions, and here are a few we'll actually dive into today. The first is, why are we using C? Why are we using this kind of ancient language to start off programming with? And how do we learn and read its syntax here? How can we actually learn how to create and read these variables, these loops and conditionals, and so on? As we go through that, we'll talk about this particular instance of it like a data type, because C requires us to tell what type each pieces of our data are. We'll also talk about compiling C programs, taking them from source code to machine code. And then finally, at the very end, we'll talk about how many years it will take to double our number of llamas that we have in the lab. So to kick things off here, we can go back to actually lecture 0 and think back to our contacts application. So in this application, we stored kind of names and phone numbers and other things too. What else could we store in a contacts application? Could I ask maybe somebody from the second row and this middle row here, what could we store in a contacts application? Yeah, go ahead.
Phone numbers.
Phone numbers, right? Other things too. Maybe somebody in the row up now. Emails, OK. Other things. Let's go one more row up again. What else can we store? Addresses, nice. So all these things we can store in our contacts application. But let's say we want to store the number of times I want to actually have made a call before in my application on my phone, right? So here we have, an instance of a variable, some number or some value that can change. And I'm going to give a name to it, in this case, calls, the number of times I've called somebody here. So this is our like mental representation of what a variable is. It's some name for a value that can change. But in C, we have this particular syntax that we use to make variables. And as you all go through and work on the course's problem set, build your own programs, you really should get familiar with the syntax and how to read and write it here. So here we have the syntax in C to create this variable named calls. And there's some components to it that we should actually dive into here. So the first part is the variable's name. This name is calls. Notice how it's in the middle of this kind of sentence here. We also have the variable's type, this int type. And what does this int type stand for? What kind of number are we going to store in here? Could I ask somebody from down here? Yeah, go ahead. An integer, so a whole number, right? Then we have the value, in this case 4, that value we're putting inside this variable here. But there's one piece we're missing we haven't talked about yet. What haven't we named here yet? Could I ask somebody from maybe this side of the room? Take a guess. We talked about the name of the variable, the type, the value. What syntax haven't we shown yet? Yeah, go ahead. The semicolon, right? So this is a statement in C. And every closing statement that we have, we want to include a semicolon there. The other thing we haven't talked about, the one piece we haven't talked about here, could I ask somebody from down here now? We have the semicolon, the value, the name, the data type. One more thing, yeah? The equal sign. And is it an equal sign, could I ask you? No, you're shaking your head. It's an assignment operator, right? So we'll say this is going to assign the value 4 to the space we've created for this variable named call. So if we say this in English here, we're going to create an integer variable. Notice how this type aligns with this type here. Named calls, the name lines up here, that gets, or that kind of stores this value 4 in this instance. So let's try it again with another value here. Int x equals sign 50. And let's actually say this one all together if we could. How do we say we create a what? Integer that called x that gets the value 50. Nice. That's what it'll be in English here. Amazing. Yeah, high fives all around. So why does C care so much about data types, though? Like the very first thing we say here is not the name of the variable, but actually the data type. So we saw briefly this idea in lecture, but let's go ahead and talk to the person next to you. Why do you think C cares so much about these data types? Why is it the first thing we tell the computer when we make this variable here? We'll come back in just a minute. OK, let's come back and hear some ideas for why does C care so much about data types? Why is it the very first thing we put in a given line of code to make a variable in this case? And can we go back to maybe this side of the room now? And would anyone in particular like to share what your group talked about, what ideas you had for this question here? Yeah, go ahead.
Basically, we said that C wants to know about data types in order to restrict the values that we can input. For instance, if we're talking about integers, you can input 3.5, so for a real number, you could. So it limits integer values.
Yeah, there's some value for like specificity, right? I want to be able to make sure that I'm not putting in some value I couldn't store in this variable, like a text, for example. Other reasons, too. Could we go to maybe down here? Yeah.
The computer needs to know how much memory to allocate to whatever you want to do.
Yeah, and why would that matter? Can I ask you, like, get a little deeper, too? Like, why does the size matter?
Because I think an integer would use a lot less size than a lot less memory than, let's say, a string.
Totally. So using or storing different values makes that value take up a different space in computer's memory. So integers take up maybe 32 bits, but a character might take up only 8 bits. And so it tells the compiler how much memory, how much space to reserve here, too. One other reason that we saw a little bit in lecture as well is we have some binary here, these 8 bits that can represent a certain, well, really anything. What does this represent here? Anyone know off the top of their head? Yeah? Oh, no, OK. I'd be surprised if you do, but one thing this represents is the number, or the integer 65, right? But as we saw in lecture a little bit too, is this can also represent the letter A. Like those same binary bits can represent both 65 and this character A. So it's important we tell C which thing we're talking about here by giving us our data types. So that's the reason we have these data types here. If we want to go further into variables, we can update them if we'd like. And here we have on this very first line the declaration and initialization of this variable calls. And down below, we just kind of update that value. So notice the type is on that top line, but it's not on that next line. And why would that be? If I can ask somebody from this side of the room now. Why is it on that top line, but not that second line? Yeah, go ahead.
Because on the first
Yeah, so the computer's pretty good at remembering things, right? And once you've told it that this variable has a certain type, no need to tell it again. It already knows that. We can just keep going as we go. So here, we're going to initialize and declare the variable calls, but when we use it again, we don't have to tell it the type as we go through. Now, if we wanted to change that value, we could do it like this. We also have some operators at our disposal. We could add 1 to it using this plus sign. We could even subtract some numbers. We could maybe multiply some numbers using that star operator. We could even divide some numbers and so on. So feel free to take a look at those as we go through the course. I'm sure these come top of your head as we go through. But when it comes to assigning some variable, what looks like a function, right, that's where things get a little bit weird. We saw in lecture we're trying to get some input from a user, right? And we didn't say that maybe string name equals, quote, Carter. We said it equals this maybe function, getString, or here if we wanted to store a value in calls, getInt. And in this case, before we're reading left to right, but in this case, it's actually better to read right to left when you see this function call on the right-hand side. So what's happening here is when you have this function on the right-hand side, this function is going to run and then give us back some return value that will be stored inside this variable on the left-hand side. So before anything else, we run this function on the right-hand side with some certain arguments, some inputs to that function, tell it what exactly to do. That function runs. Maybe it asks the user for this integer number here. And we then store that value right where that function was called. And it then goes into that variable. And now we're back to simple variable assignment here. So usually, if you're simply assigning numbers, you can read left to right. But if you have these function calls, best to read right to left, and knowing that your function runs first and then assigns that value as we go through. So questions on this before we dive even deeper? Anything here? Seeing none. OK. So now that we have these values stored in these variables, it's probably worthwhile to think about how we print them to the screen. And here's what we saw a little bit in lecture as well, this percent and then this kind of I here. And what is this doing for us? Could I ask somebody from this maybe middle section here? Let's go to the first row if you don't mind. Yeah. Yeah, placeholder for variable calls. And why is it percent I? Do you know? Because, yeah. Right, so percent I. This percent is kind of saying, like, hey, this is a placeholder, and that I specifies what kind of variable can go inside of that placeholder there. So because calls is an integer, it's percent I. And that's called, more specifically, a format code, as you might have said. And we have this value that we can store in that format code there. We could have multiple format codes and multiple values. We just separate them by commas. So you can imagine, for example, I have percent I here and maybe percent I later on. I could have calls and then comma, some other variable. And those would go inside those placeholders kind of one by one, aligning with whatever order I put them in as we go through. Now, it's not worth memorizing any of these, but there are a great number of format codes for different data types. And as you work with a variety of data types, it's best to maybe reference these once in a while. So here on the left-hand side, we have number format codes like ints and longs, floats and doubles. And on the right-hand side, some chars and strings, where chars are individual characters and strings are collections of characters as we go through. One thing we haven't quite seen as much yet is this long and double. Anyone want to hazard a guess as to what that might be here? Could I ask somebody from this middle row again? What is this long and double doing for us? Yeah, go ahead. Yeah, exactly. So here, we had an integer that could store up to 4 billion values. But when that's not enough, we might want to have a longer value, in this case called a long, that will have twice as much space for us. We can store twice as many different combinations as we go through. Or really more than that, we're just having twice as many bits to represent that information. And similarly, for the float, that's a decimal number. But this double is called a double precision floating point. So we'd have twice as many decimals, twice as many binary digits representing that decimal number there for us as well. So just more space for us to use as we go through. Now, what we'll do here is a brief exercise. And I invite you to load up code.cs50.io on your own laptop here. and you should see something that looks a bit like this. Maybe you have a file explorer on the left-hand side. But you should certainly have a terminal down below. I see a question. Yeah?
I'm not sure if this was a typo or if you went on this, but if you go back to the previous slide,
Yeah.
so the double says at and the float says at. Is that correct?
That is correct. So both the float and the double have the same format code. Yeah, good question. How does the computer recognize each one? In this case, it doesn't quite matter, because in this case, the float and the double are both decimal numbers. And so the computer knows when it sees %f, I'm printing a decimal number. It just so happens to be that the double is twice as long. And so it just prints that many more. Well, it can print that many more spaces after decimal point if you'd like it to. Yeah, other questions here before we move on? All right. So we'll work on a brief exercise here. And once you've loaded up your IDE in code.cs50.io, you go ahead and create an application called phonebook.c. And the goal is to prompt the user for these 3 things, and then print them back out to the user as confirmation that this data is stored in your program. So if I wanted to do this, I would first go down to my terminal down below, and I would make a new file. What would I do to make a new file down here? Could I ask somebody from maybe this kind of right-hand bottom side? How can I make a new file in this program here? Yeah. Yeah, code in the file name. So I could do code, if it will load here. Let me refresh. But on your own, you could certainly do code and then the file name here. And for our purposes, I'll do code space maybe phonebook.c, but you could call your program whatever else you'd like to call it here. And maybe yours is doing the same thing. We'll be back in just a minute here. Now, once you have your file, what tends to go at the very top of that file? What's the first thing you might add? We saw this in lecture. Yeah, go ahead. The header files, or these libraries, right? And do you remember the syntax for that? Yeah, hashtag include, this little caret thing. Let's see if this one is loaded now. Not quite. But this hashtag include is saying I'm going to try to get some file in my computer's memory that has these functions declared for me that I will then use in my own program here. So what 2 header files might you want to include in your program here? Yeah. Nice. So 2 off the bat that you'll often want to use are standardio.h or stdio.h and cs50.h. Both of these have some pretty common functions you'll be using as you write your own program. And we'll wait for this to continue connecting. And what we'll actually do is now that you maybe hopefully have your file open, you have your header files at the top, we'll take some time, let's say maybe 10 minutes to work on this on our own. I'll put the slide back up. And we'll come back in those 10 minutes and share how you approach this problem. Maybe if the staff would like to run around and help you as you work, feel free to raise your hand. We'll come around and help you out. All right, let's come back. And we'll be working in a slightly different environment just because the internet is not quite what we want it to be. But we're going to make here our own phone book file. We can actually store the data we want to store. So if you remember our slide back here, we wanted to store a few different things. We wanted to store the user's name, their phone number, and I think it was their address. Let me actually take a look at that slide again. If we go back over here, a name and age and a phone number. So here we have kind of this template for our program. But what are we missing right now? We have our header files, these libraries where I have functions we're going to use. But what else are we missing in this program right here? Could I ask somebody from, yeah, down here? Int main void, right. So I'll type int main and void up here. And this just symbolizes, this is like the kind of when flag clicked block in Scratch. This is just going to be the main part of our program here. We're defining this new function called main that will be the main part of our program. Now, the first thing we want to do is probably prompt the user for some information. So what functions did you all use to get the user's name, or that contact's name we're trying to store here? Could I ask over here? Yeah, go ahead.
Get string.
Get string. And how did you make your variable in this case?
So because our variable is a string, I put string and then I titled my variable name.
Nice.
Then I said equals get string, what's your name?
Get string, what's your name? So something like this?
With this space out.
Yeah, and why would you have that space there? Just readability, right? If we don't have that space there, if we maybe remove this, the user will be typing in their name right up against that question mark there, which is not what we want to have happen here. OK, so it seems pretty logical to represent a name with a string. But how about the age here? Could I go maybe to this side of the room? How did you all work on getting the user's, the contact's age? Yeah. Uh-huh. OK. What's your age? With a space, right? And then the semicolon. Perfect. So that'll close that statement. And again, this function on the right will be called. It will run and then give us back some return value, which is whatever the user typed in, and store it inside of this variable named age. And then comes the one with some, oh yeah, question here?
Can we also write string age equals yes?
Yeah, so did you try that one here?
Yeah, like what's the difference?
Good question. So we could do either of these here. One is an integer, one is a string. But you could imagine if I later wanted to do something like this, let's say I wanted to actually increase every person's age in my phone by 1. Maybe it's their birthday next year. So I say age equals age plus 1. Is that going to work with a string, do you think? No, because I'm going to add 1 to this quote unquote, like maybe 40, for example. And I can't add numbers to strings. That's not going to happen for me. So it's best when you're making these data types to think about what you want to do with them as you work in your program here. So I want to maybe change my age as I go through. So I'll actually maybe make this an integer here and say get int instead. And now for the phone number, if you go to this middle section here, how did you all choose to represent the phone number? Yeah. Long number is equal to get long. And you just asked maybe, like, what's your phone number? Yeah. And I think I'm most curious here about why you chose a long. Like, why would you have that? Yeah.
Because it's more than 2 billion, so you need the extra data.
Yeah, so a phone number is what, maybe 10 digits long? And so if I had any phone number that begins with anything higher than 2, that's going to be higher than 2 billion, which is the highest positive number I can represent with an integer. So I want to actually have a long here. Yeah, question? You absolutely could use a string. And why would maybe you advocate for using a string? Nice, so hyphens. You could also include, if you're maybe in different countries, like +1 for this like country code, plus other country codes as well. You could even have parentheses if you'd like to put the area code in front. Yeah.
Also, I think that if you use an integer or a long, you are supposing to be able to calculate stuff based on that number.
Mm-hmm.
And usually you don't add stuff or divide the phone number, so there is no like actual purpose to ask for that number.
Yeah, definitely. So we tend not to add things to phone numbers. So why store it as a number we could add things to or subtract things to or divide or whatever we'd like, right? Good question there. So we have it as a string here. The string also preserves things like leading zeros. Like maybe there's an odd chance that somebody has a 000 number, and we could store that with a string, but not, for example, a long. We tend to remove those leading zeros in that case. Yeah?
Would anything happen if you use long for the integer when it doesn't really require that?
If I were to say like maybe long age here,
Yeah.
and maybe get long to have parity, nothing bad would happen here. I'm probably just using twice as much space as I would need to. So generally, I don't think people have an age above 2 billion, and so I would probably want to just use a regular integer to store that value. Nice. Other questions on these representations of this information here? OK, so we'll go with this integer. And then just real quickly to review our format code. So let's say I wanted to print out some of this data. I could say printf. And let's say maybe age is, what would I then say? Maybe just call it out. %i, OK. Age is %i. Maybe I'll put period here. Name is %s. And let's go ahead and say phone number is %s. All right. And now to store this, as we saw earlier, I could simply just kind of put these variables in the same order. I want them to show up in those placeholders here. So I could say, OK, age is first. So I'll say age. Then name, so I'll say name. And then finally number, so I'll say number, and close everything out with the semicolon here. And if I were to make this, that is type make phone book and run it, I would then see this information prints back out to me on the screen as such. So questions on this before we move on? All right. So one of the other building blocks that we have, besides these variables and representations here, are these conditionals and these loops. And we saw these in lecture as well, but we'll use these now for the course's lab that we'll work on together. So first thing here, we have this question. Have I called less than one time? And if I have, then I'll say call more often. But just to get some vocabulary down here, this on the inside of that conditional is our Boolean expression. It's either yes or no. Have I called less than one time or not? On the outside here is that conditional itself. So conditionals have these Boolean expressions on the inside of them. I could make this a little more advanced, though, and I could have this else in the middle. And what would that do for me? Could I ever execute these two things at the same time? Could I ask over here? Could I ever do these two things at the same time? Shaking your head, no. Right. So these two things are mutually exclusive. If I have this else here, I'm saying it's either one or the other. If calls is less than one, I will do that first thing. If it's not, I will do that second thing. You can kind of chain these statements together. If you saw even in Scratch, you could say if, and then else if, and then else if, and finally this long else. In general, we have these if statements followed by these else if statements, followed by, if you need them, that final else to say like a catch-all for everything else that we could have happen here. For loops, though, if you want to do something multiple times, we have something like a bit like this while loop. And what would this print to the screen? Could I ask somebody from maybe this side of the room? What would you see on the screen with this loop here? Yeah, go ahead.
0, 1, 2, 3, up to 9.
Up to 9. And why not the 10?
Because it's while I is less than 10.
Nice. Yeah, so we wouldn't see the 10 because we're going to stop while we're going to stop if this is not true. And so 10 is not less than 10, so we would stop and we wouldn't do the code on the inside, right? So to break things down even further, we have our initialization of this loop. I is first set to 0. Then we have our Boolean expression, this question we're going to ask, either yes or no. Is this case true or is it not? And then finally, this incrementation, changing that value as we go through. And finally, when our Boolean expression is no longer true, we will not be inside of that loop there. This is really handy. We can actually try to make our code run a certain number of times. And this is so handy that C actually has our own syntax to write this kind of loop in even abbreviated format. So here we call a for loop that has all those same elements, but now just on one clean line. We have this initialization, this Boolean expression, and then this incrementation here. And we'll do whatever piece of code is on the inside as long as this Boolean expression is true. So questions on this kind of syntax for these loops? Doing pretty good. And finally, if we wanted to get a little more advanced, we have this do. Yeah, go ahead. Yeah. Good question. So you saw the int here? And why is that there, right? Because previously we had the int I already done for us, right? So these are actually kind of two different contexts. So here I have created this variable named I, and I'm going to use it inside of this loop. And this variable I, because it's outside of this while loop, will persist as we go through my program. So I could use this variable I again. In the for loop, though, if I were to create this variable I anew, I could only use it inside this for loop. I could not use it outside of that for loop. So this, as long as it's inside the for loop, I can't use whatever variable I create here outside of it. It has to be limited to the inside of that for loop there. Does that help? Great. Other questions here too? Yeah, why is there no semicolon? Well, probably the rule of thumb is this. Semicolons come after complete statements. And this for loop is kind of setting up some set of statements. It's saying, I'm going to eventually have something I want to do, but it's not there yet. So I'm going to actually have these braces to tell what statements I want to execute kind of sequentially as I go through. So you'll get used to this as you go through and write more code. But in general, statements end with the semicolon, but things that set up statements generally don't. They might have these braces. Yeah. Yeah.
So you mentioned just to clarify, you mentioned that the variable I only exists within the for loop.
Exactly.
So does that mean like when you do like multiple for loops in a row, not within each other, you can keep using I?
Yeah, it's a good question. So let's say if I go back to my actual programming environment here. Let's say I have a loop. And I'm going to say for int I equals 0, I is less than 10, I plus plus. So now I can access I inside of these two braces. That's something called scope. It's the scope of the variable. It persists in this space here. I can't use I out here. So I can't access it there. But I could, for example, have another for loop on the inside. I could say for int j equals I. That's totally valid because I is inside this loop. Maybe j is less than 10 in this case, and then j plus plus, and I do something else in that. And actually, j is not accessible here. I can't do that. But it is accessible inside that loop there. Right. Other questions here too? Yeah.
I'm a little confused. Like, where's the part that, like, I guess senses what I is? You know, like, it kind of just appears. I'm a bit confused about that.
Yeah, and can you tell me more about what you mean by like senses what I is?
Right. So, because this is like, it's like a Boolean expression, right? Like, whether I is greater than 1 or less than 1, like that kind of thing. So,
Yeah.
like, where's the input of whether it's going to be 1 or what value it is?
Yeah, so probably best to think of it like this, where my code is read top to bottom. And when it gets to this for loop, it's read kind of left to right. So the first time I get to this for loop, I'm going to make this variable I and set it to 0. Then I'm going to ask the question, is I less than 10? OK, it is. So I'll actually go inside this for loop and maybe run this code on the inside. Once I get to the bottom of this for loop here, I'll then go to the top. And I'll do this. I'll increase I by 1. And I'll ask the question again, is I less than 10? It is. OK, I'll do this code again. Once it finishes, I'll increase I by 1 again, ask the question, keep going, and keep going. Does that help?
Yeah, OK, got it. So the input was I equals 0 at first, and then after.
Exactly. This is our initialization. This is like the first time the for loop runs, set it to this value. Every time this code on the inside finishes running, ask, or actually before we start running this code, ask this question. If this is true, run this code. And when we get to the bottom, increase I by 1, or do whatever is here. Yeah. This should do it 10 times, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. It won't do 10 because that is not less than 10.
Okay. Is this called a do while?
This is called a for loop, just because of the for on the right there. Yeah. But we do have the do while loop. We could go just quickly to that one here. The do while loop has the words do while in it, right? And what this is going to do is actually not ask a question first, just unconditionally run this piece of code, and then ask the question later. And this is handy if you're trying to get some input from the user, because it'll always ask the user that question, what input do you want to give me, and then maybe reprompt them depending on whether that input is invalid or not what you want it to be. Right? So down here, we would say, this is the condition under which our input is invalid, and we should go back up and do it all over again. So questions on these kinds of loops still? Yeah.
Would this be good, like the do while loop, if you were to, I don't know, if you were asking a question within the while loop, if it is, say you're doing a certain age, and if you're seeing within a given age range, like in the while loop, you give a given number, would there be an easier way to like terminate the function if, say, you don't enter the right age?
And by terminate, do you mean like
Terminate the function, like it just stops. Like if you use like, say you're looking for the age range from like 25 to 30,
Mm-hmm.
and then if it's in there, you go to the while loop. Would you then have like the while loop? Would there be a way to kind of like stop the while loop from continuing?
Yeah, and so if I am understanding what you're asking correctly, it's often better to check for what we don't want to have happen than to check for what it is we do want to have happen. So for example, I might not want to do this. I might not want to say int age is getInt age here, and then ask the question, if, let's say, age is between, what did you say, like 15 and 20?
Yeah.
If age is between 15 and 20, then do the rest of my program. Because what I'm doing here is I'm kind of separating my program from, like indenting it by a lot, and maybe I have more conditions. Like maybe I also want to say if the name starts with A, and then it keeps getting more and more indented. So what I could do instead is I could do something like this. I could say, well, let me do this. Let me create this variable named age. Let me get some value for it. Whoops. Let me get some value for it. And while the age is not what I want, let me keep re-prompting. Is that answering your question?
Yeah, kind of, yeah.
OK. So age is like less than 15, or age is greater than 20. Let me re-prompt. Right. OK. Yeah. Probably depends on the context. So the question was, is it better to style to use this less than or this less than or equal to? In general, when you're writing your for loops, where you just want something to repeat a certain number of times, we tend to use the less than and always start at 0. So let's say I want something to repeat 5 times. I'll say int I equals 0. I is less than 5, I plus plus. And the math on this just works, right? 0, 1, 2, 3, 4. That's 5 times. If I were to do something like this, let's say int I is 1, then I'd have to do less than or equal to 5. And because programmers start counting at 0, meaning this like absence of anything is starting from the very basics, we're not going to actually have this less than or equal to sign here. Is that helpful? Yeah. OK. All right. So with these building blocks of these loops, we'll spend some time working on our lab for the next 10 minutes or so. In our lab, if I go back to my slides here, we're going to be asking this question of how many llamas do we currently have, and how many years will it take us to get to an aspirational number of llamas, some goal number of llamas for ourselves here. So if we look at this, you can find the lab at this URL right here. It's on the course website. Go to the lab page. And in that lab, you'll find these questions. Actually, sorry. Within this lab page, you're going to work on this problem kind of all together. But we'll get started working on this kind of up front here. So the first thing that we'll do for this lab is think about how we're going to work an example ourselves, and then kind of walk through and write our code. When you're working on your problems, it's often good to think about how you're going to write your algorithm first, and then write your code. So these 7 steps can help you, whether you're working on the lab, in the problem set, or so on. And notice how more than half of these are about writing things down, thinking through them, not necessarily programming. But these final 3 steps are all about translating that idea into code. So we'll do a bit of that here today. If we look at our llamas, we have a certain number of llamas. We want to figure out how many years it will take to get to another number of llamas. And we know that every year, maybe 1/3 of our llamas are born, and 1/4 of our llamas sadly pass away, right? And let's take a look at this particular example here. We have 12 llamas. And so in this current year, 12/3 new llamas will be born, and 12/4 llamas will pass away. And the question is, how many years will it take to get to 13 llamas. So to work this example, we have these 12 llamas. And now what would we do? We want to birth a third more llamas. So how many more would we add here? 4. OK, let's add 4. And how many would pass away? 3. So we'll take away 3 here. And we are at 13 llamas now, right? And that was 1 year overall. We birthed our 4 more llamas, and 3 llamas passed away. Now we're at 13. So as you go and write this program, we'll get started up here in a minute. We want to first prompt the user for the starting number of llamas, ask them for a goal number of llamas, and then do some math, perhaps in a loop, to figure out how many years it will take to get to that goal number of llamas, and finally print out that number of years. So if you are in your code space, you might go over to your environment here. You might type code population.c to open up that file. Here I have mine. You might then type include standard.io.h to print something to the screen later on. And you might also do the CS50 library, cs50.h here as well. What else do we need for this boilerplate code? Int main void, right? So I'll say int main void. And I'll leave kind of this rest up to you, but make sure you're prompting the user for a starting number of llamas, prompting them for an ending number of llamas, and then finally, maybe using some kind of loop to figure out how many years it will take to get to the goal. And keep in mind that every year, a third of our current llamas are born, and a quarter pass away. All right, so we'll work on this for, let's say, 10 minutes or so, and we'll come back and work the example together. OK, so I hope you've made some good progress on this lab. Let's come back and work the example together. We had a few steps to work through, the first one being prompting the user for a starting number of llamas. And could I ask maybe a group from this side of the room, maybe towards the back if you don't mind, how did you prompt the user for your starting number of llamas? Yeah, go ahead.
So first we initiated an int called start.
Yeah.
And we ran a do while loop. So it said start equals get int, and then start size. And then the condition was while start was less than 9.
Gotcha. So while start is less than 9. And why did you choose less than 9 for that case?
Because the lab said that the minimum number that the start size could be was 9, or else the population would fail to grow.
Right. So we want to reprompt the user if they give us a number less than 9, right? OK, that seems pretty good. And then similarly, how could we prompt them for an ending number of llamas? Could I ask maybe in the middle this time, somebody from maybe the back few rows, how did you try to prompt for an ending number of llamas here? Yeah, go ahead.
I created an int variable called n,
Nice.
and then I used a do while loop.
Yep.
Inside the loop, I had an n equals get int, and then n start.
Uh-huh.
And then the condition for the while was while n was less than start.
Yeah, and then just to ask you, why would you have that in your conditional down there?
Because in the lab, it wanted us to keep prompting if the ending size that the user inputs is less than the starting size.
Yeah, totally. So we can't have fewer llamas than we began with. So just checking to make sure that that is the case here. And if not, we reprompt the user. OK. And then our final bit down here was keeping track of how many years it will take to get to our goal number of llamas, now stored in this variable called end. And how did you all choose to represent the year, or how many years have passed in your program? Could I ask somebody from this side of the room now? What kind of variable did you use to count the number of years here? Maybe somebody from the first few rows? Yeah, go ahead. As an integer. And did you give it a special name or anything? Or int years. OK. And what did you set it first to? 0. OK. And now we have some math to do. If we look maybe this group doesn't mind, how did you all add llamas, subtract them? How did you adjust your population of llamas as the years went on? Any ideas for how you might do it or how you did do it? Yeah, go ahead.
Just added 1/12 llama each year.
Added 1/12 llamas each year. Nice. So can you tell me, if we look at our program here, we have a starting number of llamas. So how would you adjust that here?
We would go, what did you say it as?
Start.
We could do start equals, or sorry, plus equals,
Start plus equals.
start divided by 12.
Start divided by 12. OK. And how did you get start divided by 12? Like, what kind of math did you do to get there?
Common denominator of 1/3, 1/4, and then you're adding 1/3 and subtracting 1/3.
Nice. So ultimately, every year, we're just adding 1/12 new llamas after we kind of add a third and subtract a fourth. It comes out to 1/12 new llamas every year. OK, but we need some kind of loop to run this. And anyone want to help me out here with this final piece? How do we have the loop to increase this llama and know when to stop, too? Yeah.
You could do while start is less than.
Uh-huh.
Start, and then after that, add one.
Yeah, and so like add 1 to year. Yeah, so we could say years plus plus for increase years by 1. OK. And then at the very end, we ultimately want to print out the number of years. So I'll say printf %i. And maybe just to clarify, years %i, and then years down at the bottom here with a \n at the end. And if I make this, make population, run /population, I'll type in maybe 12 and 13, and I get 1 year as we expected. Yeah, question or comment?
What is the plus equal, the start plus equals start?
Good question. This is basically shorthand for doing this. I could say start equals start plus start over 12, because I'm trying to add to start as we go through. So this plus equals is simply saying, let me add to what start currently is this value on the right-hand side. Does that make sense? Gotcha. Now, there's one question here, which is, let's say I have, oh yeah, go ahead. Somewhere over here. Yeah.
Yeah, I have a question regarding the start divided by 12.
Mm-hmm.
Because we have one part that is the lemmas that are formed, and one part that is the lemmas that are time.
Mm-hmm.
Therefore, you need to round the first part and then round the second part, because you cannot have like half a lemma dying
Yes.
and 1/3 being alive. So in some cases where the number is divisible by one part of it and not divisible by the other, could create some difference.
Yeah, so maybe it is better for us to add start over 3 and then subtract maybe start over 4
Yeah, but we
and
need
keep
to
going.
round these numbers,
Mm.
because divided by 3 could create, I don't know, 3.3333, so you need to round it to 3, because otherwise you cannot like have 1/3 of a lemma being formed.
Yeah, we don't want 1/3 of a llama, so we got to round this in some way. And I think what we want to do is always round down, which brings us to some feature, or in some cases a bug in C, you might run into this, called truncation. And we didn't see this as much in lecture, but just to highlight it here, in C, when you divide two integers, you will always get back an integer. So if I divide perhaps maybe 2 and 3, 2 divided by 3, both integers, I won't get 2/3, I'll get 0. I'll always round down, cut off the rest of that data there. So to show an example of this, I might do code truncation.c. And I will have the same boilerplate code, standard.io.h. I'll include cs50.h. And I'll say int main void. And I'll type in maybe int a is, let's say, 2. Int b is 3. And let's print out the result of dividing them like this. Let's say, actually, sorry, int c is a divided by b. And I'll say this gets the result c here. I'll say make truncation and do /truncation. And I'll get 0 and not 2/3. So always rounding down here. If I do want the decimal, though, what I can do is I can convert on the fly one of these to a decimal. So I could say, actually, I want a to be a float, and then complete this division. And as long as one of your numbers is a float, you'll get a float in the very end. So I'll say maybe %f here. I'll do make truncation. Whoops, let me say this is actually now a float in the end. Make truncation. I'll say /truncation, and I will get that 0.6667. If I were to not do this, I would get 0 all around. So just something to keep in mind as we go through here. Happy to stick around and answer any questions that you all have, but this should bring us to the end of our lab today and our super section as well. Thank you all for coming. It was wonderful to see you here. Hope to see you next week in section.